Just about to start in 1 minute. Should be good in 1 minute. Just gonna wait and see the delay.
Give me co-authorship credit for those definitions. I see how it is.
Sorry. VJ Vanessa helped define 2 things in this presentation.
Yeah.
So you can all thank him for that.
Not much of that.
We have the broadcast up yet, Steve? You want to actually look at that?
Oh,
Help me out here.
Sorry, I was trying to create the program. Okay, so
Yep. Okay.
it says live.
Yeah, I see that. Thank you.
Yeah.
Okay. We are.
Sure.
Okay, so I'm going to start. Hi, my name is Ian Guile. I'm presenting basic reverse engineering concept, methodologies, tools, examples. So I just wanted to start off with this quote. The difference between a master and a beginner is that the master has failed more times than the beginner has ever tried. That being said, I'm not a master, nor do I claim to be. However, I've learned a great deal by failing time and time again and learning it on that last try. And so I just want to say everyone should do the same, because that is how you will learn best. And if you don't at least try, you're never going to be able to succeed. So if you're afraid of failing, get over it. It's not going to get you anywhere. You just have to go for it. Okay, so why reverse engineer? Capture the flag events very commonly have reverse engineering challenges. It's a great thing to work on. Applications don't always do what you want them to. And by learning reverse engineering, you will get a much deeper understanding of applications and how they work. What we'll be going over, we're going over basic reverse engineering in Windows. You can definitely reverse engineer in Unix, Linux, on a Mac, on whatever. But for today, we're going over Windows. I'm going to be using Immunity Debugger, program called Detected Easy, the Hex Editor Neo, Sublime Text. And I'm going to be going over applications. That's actually wrong. That's going to be 1 through 7, which have all been written by Joe Guile. The first step in any reverse engineering challenge is just to determine what you're looking for. In CTFs, they're called flags. So the first thing you're going to do is initial analysis. Everything you do when you're doing reverse engineering should be done inside a virtual machine. This is for your own computer safety. Otherwise, you can get malware or all sorts of other problems. I have opened the first application in the program Detected Easy, and we can see here that the program is an executable, which you can see right here, and as well as up here. Bye. We can also see that the program was written in Visual Basic, which we can see right here. From here, we're just going to assume that all the applications tonight that I'm going to work with are completely safe and non-malicious. For CTFs, most of the time this is the case. However, if you are reverse engineering your own software or reverse engineering malware, that's when the VM is very important. Because if you don't use a VM, that's how you get malware on your machine and all the machines on your network, and so on. And that's a serious problem. Okay. Now we run the program and test it. In CTFs, which all of these applications were from, they were from a CTF called Root the Box here in Arizona. The goal was to get the flags. And so we want to take a look at the application, see how it runs, see how it works, kind of get a good idea of how to approach the problem to see where we can start reverse engineering it from. Okay, so here we can see that the program is asking for a password. I tried 1, 2, 3, 4, and it told me that I was wrong. Also can see that the maximum length of characters in the program, and After that, we can also see that after trying 3 times, just including password and QWERTY, that none of those work. And the program will then just close out. It'll say too many attempts. You click that OK box and program exits out. It's gone. So you have to restart it and try again. So because we're looking for a password to enter into the text box, we should just start with the very basic, which is just looking at strings that exist in the program. The program detected easy, or in this case, I'm just going to call it die. It's able to pull out more strings than any other program I've tried. I've tried a few, including just the strings command, and detected easy does a really, really good job at that.
It really is fantastic.
Yeah.
I recommend it also.
Yeah, it's one of the best tools for reverse engineering I've found yet, and it's free. I mean, you can't beat that. It's called Detected Easy, so the abbreviation is die. Yeah.
And the Windows version is actually better than the Linux version.
The Windows version has a very easy to use GUI and all sorts of other things. The Linux version is okay. I haven't experimented with it too much yet. So opening up the first application and looking at the strings, we can see that the ANSI or ASCII strings on the left, we can see some various different strings here. But for the most part, they all look like they're either not helpful, like these over here. These are not going to be of any use to us. Now, we can keep in mind that the password could be one of those, but it's also pretty rare because they just look like not proper strings. And we also see things like a form password. We see that that's what he named the program. We can see like a form, which in Visual Basic is what you call the entire window. We see a few various other like commands. So then I'm going to take a look at the Unicode strings, in which we see some other strings here, including a string called way too easy. So, well, we'll try that. And what do you know? That was it. So we got the password or the flag, which was VB critical. It was that easy. That's one of the easier reverse engineering challenges I have seen. It gets more and more complicated from there. And for the second one can be solved exactly the same way as the first. However, that's no fun. So we're going to go over another way to look at it, and we're going to mess with the program itself also. So here I have it opened up in Hex Editor Neo free, which you can get for free. It's a great hex editor, can do a lot. So we have the app1 on the left and app2 on the right. So I searched for way too easy in the first application and scrolled down to the same offset in the second. You guys all know what I mean by offset, right? Is that a no?
Yeah.
Okay. So basically an offset is from the beginning, it's basically how far down into the program, how many bytes. An offset is basically a difference in bytes. So I just scrolled down to the same point in the second application, which you can see on the right there. Okay, so we can see that they're pretty similar with just a few minor differences here and there. Can anyone point out the password in the second program? Maybe kind of hard to see there, but can anyone point it out? You can go up and walk up and tap it if you want, if anyone can see it. Anyone see the password? Look for similarities in between the first and the second. So you see how in the first it starts, we see this text password and then the YYY X how. Okay, now do you see where on the second side? You see where it is? You go ahead and say it. What do you see? Top Gun, that's right. Okay. Yep, so rather than typing Top Gun in, we can actually change that string to say something else. However, it's important when you do this that you don't delete anything, as that will change the offset of the program after that point. That makes the program completely useless and you can't use it after that. It just won't be able to run right. So all we have to do is just go through it, edit that. So you see how on the Top Gun, and then on the left, I actually changed it. I reopened the program after I changed it. I changed it to QWERTY. So then I went and entered QWERTY into the application, and it gave me the flag, which is Johnny Red. So just like that, you can change applications just that easy in this case. Other applications, it gets harder and harder. Okay, so for the third application, at the bottom you see a graph of the one on the far left is app 1, the middle app 2, the third one is app 3. An entropy graph is just going to show you the entropy at many points during the program. Entropy is in a way, it's a graph of the somewhat randomness of the program itself. And it's also the ability to be predictable. It's pretty complicated, and it's can get much more in depth into the entropy. There are many more uses for the entropy graph. I'm going to do that later. Okay. I'm actually going to pull that up and show them. But however, we can see that the first two applications are very, very similar. The entire section, like right here and right here, like those are both very, very similar. So we can assume that they're going to operate nearly identical. There is a possibility that they're going to be quite different, but it's very low. However, we see in the third that it is very, very different. We also see that the third is much, much larger. You can see at the bottom how it's more than double. Actually, I think it's almost triple the size, which means there's probably going to be something different with the third application. And that's also in DIE. DIE pulls up those entropy graphs. I also took a look at the byte count. This is still in DIE. And I can look at the byte count, which byte, how many times it appears in the program, and the percentage that is in that program. We should expect to see a somewhat even spread, a few percentage difference here and there. That's normal. And you can easily see that in applications 1 and 2. However, in third, we see that a good 30% is, and a 20% is OXFF. So that's just the hexadecimal representation of the CO and the FF. So from there, we can assume a couple things about it. That, first of all, there may be some definite steganography in this. That is a pretty plain steganography, or that there is something quite different with this program, because that's not too normal to have that high of a percentage of those bytes. And I forgot to explain that the 00 is much more common in programs. So seeing 60% there is pretty common. Right. So when we look through the program in a hex editor, we see that there are 34,916 bytes of repeating CO and FFs with some OO bytes in between. And you can see I clipped a part of the hex editor right there. So you can see that it looks somewhat to be sort of nonsense, but that there also may be some sort of pattern, possibly. And as it says below, the OOs are going to appear as the dots, the COs are going to be the A's, and the FFs are going to be the Y's. That's just the potential ASCII translation that the hex editor did. We have no exact direction to go in. Anyone have an idea? Just spitballing. Go for it. You have an idea what to do? No? Okay. Okay, so if it's a pattern, is there anything we could do to try to maybe determine what the pattern is in the program? Well, we can throw it in a text editor called Sublime Text. Sublime Text, in my opinion, is one of the most powerful text editors out there. It is fantastic to use. It's just great. So using Sublime Text, we can see that COFFCO is repeated over 10,000 times, and the OOOFF is repeated almost 1,500 times. We can shorten the amount that we see this by replacing the first pattern with a space and the second with a 1. This basically just shrinks it down because otherwise we're dealing with about 10,000. What was it? It was 34,000 bytes of that repeating pattern. So by shortening it, we can basically make it look a lot more condensed and really see if we could see that pattern more easily. So here it is inside of Sublime Text. We can definitely see that there's some sort of pattern here. Any ideas on how we could further clean this up? Anyone? Okay, well, we see this kind of cascading sort of zeros at this point. So anyone have like some input? What would you guys say to do with these zeros? Have any ideas?
What's that?
Not quite. They're actually, we actually are going to have to use them. We can actually use them to line them up. It's actually, it's a set length across. And so when we set all the zeros to actually, I just set it to a single character and then put a return at the beginning of every set of zeros. So I just entered right before the zeros. We actually see this. And yeah, those are letters. Yep, that's right. It's upside down. So if we reverse the lines, which we can do in Sublime Text with just one command, we get this. Yeah. So that was embedded in the program.
And the first time Ian wrote a program to do this.
Yeah, I actually wrote a program that ripped the hex out of the application and then translated that into an image and displayed the image. But that was the way unnecessary hard way to do it. It can be done much quicker like this. Okay, congratulations. We've got the first 3 flags. Now, that took a matter of minutes for me to go through, and I know I went through that kind of fast. However, it took me hours the first time. It took me hours and hours. Reverse engineering is one of those things that when you go through, it's going to take you a long time starting out to get anywhere with it. But then as soon as you figure out what it is, you're going to hit yourself over the head just knowing that it was that simple all along. Yeah, so it can take hours. I think it took me like 2 or 3 days to finish those. The first 2 were solved the same way, so that was really quick, and it took me quite a while to work on the third one. So yeah, it can take a long time to get there, but don't be discouraged. Again, like with the quote I said at the beginning, if you're afraid to fail, you're not going to get anywhere. You just have to keep trying, figure it out, keep pushing on. You'll end up getting it. And work in a team. It's great. Other people can throw ideas around and they can definitely help. Okay, so now I'm going to do an introduction to assembly. I'm going to be using Immunity Debugger for the disassembly of the applications because from here on, there's no explicitly easy way to just flat out rip the passwords out of the programs. We are going to have to disassemble them and use a debugger or something else to actually get those. So in this case, this is Immunity Debugger. The top left, we can see the CPU. Top right, we can see the registers. Bottom left, we can see the hex dump. Bottom right, we can see the stack. I can explain all those. Okay, so the registers, there are sections of memory that can be quickly accessed on the CPU die. Some instructions like the EIP and ESP are used for pointing to locations in memory, while the majority of the other registers are used for just general purposes. There are also flag registers that can state various information. Those are used by certain instructions like compare and quite a few others. The stack is simply, it's a section of memory that contains currently used data. It can actually be a lot more complex than that, but in summation, it's that. So here are the registers, and this is all for x86. So that's 32-bit assembly. We're not going to touch 64-bit. That introduces a few other things. EAX is the primary accumulator. It stores functions for return values. ECX is the count register. EDX is the data register. EBX base register. ESP, as I said before, is a stack pointer. EBP is the base pointer. ESI is source index. EDI destination index, and EIP. A couple of the important ones are going to be EIP. That's going to point to the next instruction to execute. That's going to be possibly one of the most used instructions or the registers that you'll look at. That'll just tell you what's going to happen next. Where's it going next? EAX, it's one of the most used registers. It can store data. It's primarily used for mathematical functions, so adding, subtracting, XORing, ORing, ANDing, any of them. Count register for string and loop operations. They all have their own purposes, but they can, apart from ESP, EDI, and EIP, they are all primarily general. The common instructions for assembly, these are a lot. And by the way, if you guys have any questions at any point, just raise your hand or say, hey, wait up a minute, and I'll be glad to go further into depth or simplify it for you guys, whatever works. So some common instructions are NOP. That just means no operation. It can be used as a spacer to help align things and has a few other functions. Push moves a word, dword, or qword, or a register that is not EIP onto the stack. Pop removes a dword off the stack and puts it in a register. So you have push and pop work. They're kind of the opposite. So it moves information either onto or off of the stack. Call moves control to a different function with the purpose of it being returned back to that point. Return, or RET, is that return back from a function. And I'll show you guys examples of these too here in a minute. Move can move a register to memory, or memory to a register, or an immediate to register or an immediate to memory. LEA copies the result of one operand to another, which is an operand is register, memory, address, or a constant. CMP compares two operands and then sets a flag. However, we don't actually, for the purpose of what I'm going to be going through, we won't actually need to be analyzing the flags. There's a pretty easy way to see what that will show us. JMP just jumps. It jumps the whatever's going to happen next to a point. That can be either an absolute or relative. You guys know what the difference is? No? Okay. So relative would be relative to the current point, so which would be to jump. So that could be 4 bytes down. It could be 16 bytes down. It could be up. It could be whichever way, but it's going to be relative to that point, or it could be absolute. So from the beginning of the program.
Oh, okay.
Yeah. And then the following conditional jumps perform a jump based on the condition of the previous compare. So those are all listed down below. Any questions? No? Okay. So that's the end of these slides. So from here, we're going to do it just ourselves. So I'm just going to pull that up. If you give me one moment. Okay, so we're going to start with the fourth application. Okay, yeah, that's normally this is pretty small, which is not too much of a problem. But just 1 second. How did we get it bigger in yours, Steve? Oh, here we go.
Yeah.
There we go. That's nice and big. Everyone can see that? Okay, great. Okay, so I just need to move this so we can actually see that. Okay. So here it's actually not starting in the program yet. It's actually holding at a Windows DLL, which if everyone knows what that is, it's basically a dynamic linking library. It's a library that allows programs to work, basically. Yes, I know that's not technically correct, but he's snickering over there. But summed down, that's basically what it is. It lets the programs know what they're doing. This is such a terrible description of a DLL. Anyway, so as soon as I do that, I can actually see that this popped up here. We have the application running. We can try a couple things if we want. We can just try passwords here. None of them work. Oh, look, too many attempts. Okay, exits. So at that point, we're just going to restart it. And then we just need to play it from here. Okay, and it's back and running. So we have it here. I'm just going to pull it down to the side. Okay, so from here, we can actually pause execution of the program, which means from here, you can't see this, but I'm actually trying to open the program right now. You can't. It is, it's paused. It can't receive any input. It can't output anything. It is suspended completely. So here's how we can actually get a good look at the registers right here. So you can see all those registers I mentioned before. We can also see the flags. Those are right there. And a few other registers that we actually we won't be dealing too much with. Here's the stack. We can actually see the stack, and we can see the memory that it has right here. And these are things that it has pushed onto the stack at this point. And they can be, they're basically waiting to be popped off. And you can even see things like this, processor architecture x86. That's stuff from NTDLL. And we don't even need to worry about that. Anyway, so the first thing we're going to do is we're actually going to go to the program. Right now, we're actually waiting inside, I think, NTDLL. We're waiting inside a DLL. So we're just going to go to View, and then and that was by right-clicking. And we're going to go to App 4, which is the name of the application. And we're here. We're inside the program. And so we can actually scroll through it if we want, and it's assembly can be pretty lengthy, but we can see that it's not too short. So what we're going to do is we're going to look for something that is a reference point, because otherwise we're stuck here in the middle of nowhere going, what is this? I don't know where we are. I actually just scrolled right past the reference point we're going to, but we're going to ignore that. So we're going to search for all reference text strings. Basically, that is kind of like the strings input I ran on die. It's not as in-depth. It doesn't do as good of a job. However, it lets us refer to the specific sections or a specific point on the CPU. We can see those points right here. So all reference text strings. And we can see all the strings. We can see right here, that's where they are on the CPU. Here we can see the ASCII or Unicode. And then we can see the other strings in here. So through quite a bit of experimentation, and once again, I just want to remind you, hours, guys. This takes hours. I want to go through it in a matter of minutes. It can take forever to get through any of these applications if you don't know what you're doing. I've been working on assembly for how long? Would you say? Like
I know when you started with me.
3 months,
Yeah.
maybe. I'm still not that great at it, but I'm definitely learning. Anyway, so we're just going to go through here, and I know that incorrect password, that's what it displays when we get it wrong. We also see that it says, congratulations, the password is, oh, is it going to show us? No, it's not. That'd be nice, though. However, from that, we can just kind of draw that most likely what it's going to be doing is it's going to be generating the password, hint, that's what it's doing, and inputting that at the end of that string. We can also see access denied in too many attempts, which is what happens when we get it wrong 3 times in a row. However, I don't want to wait 3 times in a row because then after that, it's going to boot me out, and that's no fun because I have to restart it. So we're going to go with incorrect password. And so if we just double click on that, it's going to jump us right there here on the CPU. And then on the CPU, we can see the location. Here on the left, we can see the hex that Immunity is. We would be able to see this hex in this order in a hex editor. However, in Immunity, we can see it right here with the interpreted instruction of what it's doing here on the right. I'm actually going to move this register over. Okay. So from here, we kind of look around. Basically, for a little bit, whenever you get into an application and you're disassembling it, you're not like, oh, I need to go do this. I know exactly where it is, unless you've been doing this for a long time and a lot excuse me, a lot longer than I have. So the first thing is you're going to take a little contextual look around. Now, keeping in mind that it's going to be going in the downward direction. However, jumps can move the operation up from what we see. So a jump, which we can actually see here, this jump we can see by this little blue line you can barely see on there. We can see that jump is actually moving down. However, that jump could move up. It is possible. So we kind of take a look around and we can see that right here, it's making moves and then it's copying. That's what that LEA is. And then it's calling something. Move that over. There we go. Now you can see everything. So we can see that it's moving D-word onto EAX. Oh, by the way, I forgot. I'm sorry about that. Everything you see in this, it's going to go from the right to the left. So LEA right here is copying this D word onto ECX. It is not copy ECX to D word. That's very important. You're going to be very confused if you think it's the other way.
Say it again.
So, what?
Say it again.
So it's right to left on here. So this LEA, which we went over, which is copy, this is copying that D word onto ECX. You guys all know what a D word is, right? So, okay, 1 second. A good old Windows calculator. Okay, so a D word is going to be so we have a bit, which is one binary spot, which we can see right here. So that's either an O or a 1. A byte, which is 8 bits. And then we can actually go through, and as I type in just numbers up here, we can actually see this move over. I'm actually going to change that to hex because that's what we deal with primarily. And then we have, so here is this 1 digit, here's a bit, and then here's a byte up to here. And then so over to here is a word. So a word is 2 bytes. A D word is, you guessed it, a double word, 2 words. A Q word is a quad word, which is 4 words. So that's this much data. No one's going to deal in nibbles. There are many other pointless. Okay, there's a point, but we're not going to be touching nibbles or anything like that. So that's a D word. A D word is this much space, which we can actually just fill in here. And there you go. That is a D word. Everyone got that? Cool. Great. So we can see that this LEA is copying this D word over to ECX. Anyway, so we can see that this pattern is repeated very, very, very frequently up to up here. So we can just keep going up here, and then we can see that it's moving a lot of D words, and you can kind of see what it's doing. I don't see anything too interesting, so we're going to try looking down from the that point, which was right. Where is it? Why am I having trouble seeing that? Okay, right here. So incorrect password. We can set what are called breakpoints. Basically, if I double click in this section, right where the hex is, I created a breakpoint, which means when the program gets to this point, it will stop and ask me what I want to do. It basically resuspends the program when it gets to this point. Breakpoints are your friend. Use them. They're fantastic. It's awesome. You have to use them. Otherwise, you're either going to have to be a genius or I don't even know. Luckier than anyone else. So we're going to look down from this point so we can see that, oh, dang it. Well, this is a good time to show you up here. We have these different letters up here. We can see that's down in the bottom left, you can see what it's telling you. So we can see logs, modules, memory, threads, windows, handles, CPU, patches, call stack. Patches are basically what you have changed. The call stack and breakpoints. So we can actually use breakpoints as reference points. And I can just click there and I'm right back. Anyway, so we can actually keep track of our breakpoints through right there. It's very, very, very useful. So looking down, I'm just kind of looking at what it's doing. And guys, this takes a while. It was more than a month before I really started understanding what this does. So if any of you can understand this by the time I am done tonight, I will be amazed. You guys will be awesome. Yeah. But it's seriously just one of those things that you just keep looking at it and you keep going through it and you'll learn what it's doing. Like it takes a while, but you'll learn it. You'll definitely get it. Okay, so we're just going to be looking through this. And I can kind of see that it's still making those calls back. And we see a jump here. And so when we click on it, I have it enabled so it shows a line down to where it's going. Also, this whole column right here, if you see an arrow, that's an entry point. So that's basically where it enters. A $sign is a call being made to that point, just for reference. So we can see that this jump is going down to here. And again, that's a JGE. Anyone remember what that is? It's a jump if the compare before was, that's greater than or equal to. Yeah, you two can input.
No.
No? No?
You know it. So
I know. If no one says anything, speak up. Don't just leave me hanging, man.
all right, Dad.
Don't leave me hanging. Anyway, so we have this compare, and that's comparing these registers EDI to EAX, and it's going to set a flag. And based on the flag, it's going to either jump or not jump. So that seems kind of uninteresting right now. So we're just going to keep going, looking through this. While I'm scrolling down, I'm just kind of looking through what it's doing. Also, look at here. This is Immunity Debugger's comments on the program. It's telling us what it thinks it's doing or what it thinks we should know. Sometimes they are pointless and they will tell you nothing. Sometimes they are very, very helpful. Anyway, so I'm scrolling down and I'm just kind of going through this, and I see, oh, another Unicode string. Oh, well, that's the string that we saw earlier. I'm actually just going to move the registers to the side here so we can see that better. Oh, so that's where it says, congratulations, the password is. So that's pretty relevant, and if it gets that point, I'd like to know about it. So I don't want it to skip past that without me knowing. So I'm just going to set a breakpoint there. By the way, you can set tons and tons of breakpoints. It can get pretty annoying if you're not keeping track of them pretty well, but it's better to set a couple too many breakpoints than not enough, because if you don't set enough breakpoints or the correct breakpoint, you're going to totally miss it. And you could have the password staring you right in the face and you'll never see it. Anyway, so from here, we know that if it gets to this point, we have succeeded. It's going to send us that congratulations, the password is, and the string. So we can most likely assume that in between this point and I passed it. Yep, thank you. And this point, somewhere in there, the decision is made whether to stick with incorrect password or to give us the correct password. So from there, especially in this case, in the case of the apps 4 through 7, we're going to be looking for jumps and where those jumps are going to. So I'm just going to give you a hint. We can ignore that one. So I'm just going to look over these jumps and see, okay, so that one's just jumping over here. And we kind of see that it's doing some stuff. It's making these calls pretty frequently, but I can see that that's to VBA string move. So that's Visual Basic string move. So it looks like here is where it is assembling the final, from what I'm guessing it is, here's where it's assembling the final string. So the password that is actually given to us. And so if I just keep going down here, I can then see, did I completely scroll past it? Nope. Okay, so I can see here. Oh, did I change that? 1 second. Nope. Sorry. Just want to check on something. And it totally lost us again. Sorry about that. This is not a short process, guys. So as I'm going down here, I can see, oh, here's a JE. So that's a jump if equal. So that's doing this compare, which is comparing the word the DI flag. What's that? Oh, it's just comparing DI. By the way, the EAX, ECX, all those are the extended 32-bit registers. There are 16-bit registers and some 8-bit registers. In this case, the DI is a 16-bit register. That's why we don't see the EDI. That just means it's just taking up the first 16 instead of 18 bytes. Probably could have explained that a little bit earlier. Sorry. Anyway, so we see that that's making a compare, and then we have a jump right here. So we see that this jump, if this jump is taken, we can see that it skips right all the way down to here, which is skipping right past where it even can load the string that says, congratulations, the password is. That means we're going to want to put a breakpoint here to see if that jump's being taken or not when we enter the wrong password. We can probably guess that when we enter the wrong password, it's going to skip past even loading that string. However, that's not always the case. That's why we also look right here in this column. We can see that there are no entry points. Because if there was a jump here, but an entry point right here, that means it could be jumping down and then jumping right back up. So there's kind of a lot of things to keep in mind. I know, guys, and if you want me to slow down, I will. But just kind of going to go through this. So we're going to see that, and we see this jump that goes right past it all. And then we see some other the calls and moves and pushing, normal operations. Anyway, so I feel pretty confident because I've done this before. So I'm going to start the application back up. Okay, so we're going to enter ASDF because I'm lazy. We're going to submit. Okay, so right there, it hit incorrect password. It has paused the program. So I'm actually going to say, okay, and once again, because I hit the breakpoint, I can, whoops, there we go. We can actually look at all the registers and the flags and everything here, and we can look through it. We can also look at the stack and look what it has loaded onto the stack at this point. So far, nothing really of use. I don't really see anything that is of any sort of relevance. So we are going to just continue to that next jump. So assuming that I followed everything correctly, it should hit that next jump. And it did. So we are now at this jump, and we can see immunity when it's going to take the jump. So when the flag is set so that it will take the jump, this line will be blue. It's pretty hard to tell, but if it is set so that it will not take the jump, it's going to be gray. However, we can see that it's going to take the jump here, and it's going to jump right past congratulations. I'm going to run through this twice just to see how it operates if I just let it do this jump. So we're going to hit play, and it tells us incorrect password. So I'm going to do that one more time. Same password, ASDF, which I just know is wrong. Well, obviously, because it told me it was. So here we are again at incorrect password. So it seems that this is being loaded no matter what. It's just part of the loading. Hits the jump. Now, what we can actually do is we can reassemble this before it completely executes. So all we have to do is double click that. And I can change that jump if equal to jump if not equal. That means it's not going to take the jump. And we can reassemble that and then hit cancel. And then so see how it's changed. And now this line is gray. It's kind of hard to see that, I know. Sorry about that. So we can actually see that it's not taking this jump. Just 1 minute. Okay. So we are going to see if it can actually reach this point. And here's hoping. Oh, it does. It reached the congratulations. Now let's see if it's actually going to give us the password. So I'm going to hit that one more time. And let's check the app. There we go. The password is Viva La Bam. Huh? Yeah, it is. It is quite a lot of work, and like I said, hours, guys. It's not easy. It doesn't take me 5 minutes to go through this. That's because I've gone through this like 8 or 9 times now. Yes.
So you basically just decided to skip the jump to the error, to basically saying you're wrong.
Yeah.
If you put it in the right time.
So basically, I changed the jump. It did a compare, and it basically what the compare did, and I can actually run through that one more time and actually show you guys that the password actually appears on the stack too. And if you catch it on just the right moment, it'll appear in the registers. However, that is literally stepping through it one step at a time, which, by the way, it's constantly referring to DLLs. It's constantly referring to libraries. Like, we're talking thousands and thousands and thousands of times. So you're not going to step through it. It takes too long.
So now that you've changed that jump, if you put in the right password, would it jump past the congratulations since it's like no longer, if it's the right?
Yes.
Okay. So
it would actually jump right past it.
It would jump past it.
Mm-hmm. However, because we actually can see that now, now that it gives us that, we can actually go over here.
Change it back.
We can pause it. I'm going to look at the patches so I can see right here at this address space. Stop making everything so thin. Okay, so basically we can see that I changed right here I changed it from JE to JNZ. And if I click that, I can actually see that right here, this right here is 85, which means, remember how I went into that hex editor and edited the password? I can go back into a hex editor right now open up the program in just its raw hex form and change those two right there. I can change that 1 byte to an 85, and I can give that program to anyone, and they can type in whatever it is, as long as, like, as you pointed out, as long as it's not the correct password, and boom, they will get the password. Just that simple. So that's a permanent fix that actually modifies the application. There are many other ways that I could get around it. Like if I'm going to do it one more time here, which I am, I'm going to pause that, which I think it already is. And then we're going to play it. We're going to do this. We're going to submit it again one more time. And we're going to go down to the jump. And then we're going to pull up this. Here's the stack. And if I'm looking through the stack and I already know what it is, sometimes the passwords can be a little bit more less obvious. However, I can see right there, the password is Enigma Rocks. There you go. There's the password. So now I actually know the password. So I can go back through, change it back to a JE rather than a JNZ. And I can enter Enigma Rocks and it will tell me I'm right because I am. Just like that. It just gave me the password.
So how did you get access to the password?
Okay, so this is the stack. So basically, it's a whole section of memory that's reserved, or not really reserved because it can be allocated to, but it's a section of memory that is being currently used. So what the different instructions, like, let's see if I can find one. Okay, so like push pushes onto the stack, right? That's right here. So pushes onto the stack. So that's pushing something onto the top of the stack. So we can actually see that here that it's pushing EAX and it's pushing ECX and it's pushing 4 for whatever that is. I don't know. That's a whole lot more work. What?
You see a pattern like that. It's for function calls. It pushes the arguments onto the stack and then calls.
Okay, well, there you go. So for anyone that's listening in, that was VJ saying that it's for a function call, and that's what that pattern is right there. Anyway, so we got onto the stack, and then a pop, which is, where's a pop? I don't see any pops. Anyway, a pop pops it off the stack and then can put it onto a register, to which point we can see it in the register. And there's a bunch of different ways you can see it. However, we can see the password right here.
Yeah.
So that was the 4th application. That was the easiest one. That is done this way. So let's load the 5th one. And we just have to click play a couple times. Okay, so there we go. We see that this one looks a little bit different. Please enter your registration code. So we can actually go ahead and enter. I'm just going to enter A's because that is something that if that runs through the stack, or I can see that it's comparing something to an AAAA, I can see that quite clearly it is comparing my string to something, or that it's just doing something to my string in the first place. So that's a pretty common technique, is just to use just solid A's. Usually people actually use capital A's. Shame on me, but it's okay. So we're going to register. We're just going to try this straight out because this is a different program. I mean, it looks totally different. It could be completely functionally the same. We don't know, though. So we're just going to test it. Invalid registration code. So now that we know that that's the string it's going to return to us when we're wrong, we can go from there. So we're going to pause that. And then, okay, so who remembers how to get to the application itself? Well, we're currently not in the program itself. We're currently in a DLL. So we're going to need to navigate to the program. Anyone remember how to do that? We're going to go to view.
View.
Yeah.
All right. So view.
Another way that we could actually do this, I'm going to reload the application so we can see this. We can actually see that it's starting out in a DLL. So we're going to do it once, and then we can actually see that it's about to start the program. However, the program isn't started. So we can actually see this. This right here is the address where it is on the CPU. So remember 401294. Okay, so now the program's up and running right there. And so we're going to go pause, and that's 401294. And then we can hit Control G as the shortcut to jump to an expression to follow. Oh, look, it's already entered in. And we can hit OK, and then it'll just jump to that point. That's the longer way. However, that is a way that I can jump to any of these points. Just a quick way. Yeah, you just have to remember the address. But if you have been dealing with, like, people who actually do this for a living will be working on single applications they can work on applications for a long time. And so you'll learn a couple of key address points, and you'll remember, okay, I need to go to this. And if you don't want to mark it, it's just a really easy way. Control G is just basically jumps to whatever point. Or you can go to and then expression. Anyway, so but now that we're in the program, we're going to go, we're actually in the program, so it's not actually going to display here. So we're going to right click, search for all reference text strings. And does anyone remember, before I keep scrolling down, does anyone remember what we're looking for? Yeah, incorrect registration, correct. So we're going through here, seeing a couple of Unicode. Okay. So did I totally scroll past it? Nope. One second. And I totally lost where it is. Invalid registration. Which, that's a string, and that's not right.
Yeah, I was right about that.
Oh, did I really?
Yeah, I was right about that.
Oh, okay. Oh, dang it. Just 1 second. Where was it?
That was right there, around there.
Yeah.
Yeah. So if we go through here, this is actually just the string, which means it's going to like jump to that or call it just for a reference of what that string is. That's actually not quite where we want. Okay, here's the program. I'm going to move these registers over since we're not currently looking at them. Anyway, so we can see that it's just looking through it, we can see that it's making all sorts of different call and the move and the push. Again, see a couple points along here. Oh, just a second. I want to check something. And then 402, what's that? 402 BB3. I want to make sure I haven't actually, yep. Okay. I just want to make sure I hadn't actually patched this when I was working with it before and patched out that comment. So if we're going through, we're just going to try to be looking. We're not like really trying to follow every instruction at this point. We're trying to look for a reference point. So something that we can easily see that it's doing and that we can kind of have a reference point off of. I'm just going through here. And this can take a little bit. Especially because I didn't make a note of where exactly it was. My bad. So we can see that it's doing some sort of push and then copy and then push and copy. Oh my gosh. Hold on 1 minute. Sorry.
Now this also used for a capture the flag and use this as something else.
What?
Use this program really program.
Oh yeah, you can use this on anything. You could attempt to use it on even like Chrome or something. Good luck. Beyond the fact that Chrome is huge and incredibly more complex than a simple program like this.
Yeah, like another day we'll go over like some of the different tools. Like we can go over like IDA, GDB. But what did you say? Oh, your app? No.
No, we're not touching your app, VJ.
Why not?
Good is not the word for that thing.
What's wrong with you?
It's explicitly designed to give a person.
Besides it crashing my
I fixed that. No longer crashes the debugger.
Actually, that would crash the entire system, and then I have to reboot.
Hold on.
Jack all my stuff up.
What's the purpose of anti-reversing?
It was, and it did its purpose. I was like, oh, nothing works.
Applications will always be reversed. You can press the reverse engineer out long enough that will be fine. There you go. That's how to scope up this, I suppose.
We're gonna go with a yes.
So we're looking for the AAA, right?
Not at this point. That would be, we're gonna have to set a breakpoint to actually be able to ever see that.
Does Immunity do stack watching? Does Immunity not do stack watching?
You can, but I don't know how to. Yeah, I know. So invalid registration code. Actually, I'm going to reload that just because programs can be made so that they change if something is wrong, like including hiding something from you, which I would not put it past this application. And by the way, I created a zip file with all the applications and the tools I've used tonight. So if anyone wants that, I can, after I'm done, I can just take note of your email addresses and I'll send it to you. And you guys can play around with it. And I'll include the PowerPoint in that presentation as well.
Is there a way to put it on the Google, the Larry Google thing? You have the drive for them.
I don't know.
I mean, they can just join that.
I don't know.
Really easy. I'm just not knowing it.
Yeah, it would be easy. I haven't set that up yet, though. I can look into that.
Okay. Take a look.
I'm trying to go through these pretty quick, so yeah, but like I said, it can take a while to find the point, and then once you have that, it can take a while to I'm just gonna set one right there for right now, just for reference. Well, that's not right. So at this point, we could actually just slowly step through it. which I believe is what I did. Steve, were you with me yesterday when I was doing these? 5. I think I cleared the string that it gives me that I use as a reference point. I think I told it to clear out the string that I was using as a reference point.
Oh, yeah, you cleared all the stuff.
Oh, right there. There we go. See, that's what you get when you rename things, people. Don't do it. Yeah, so right there we have failure. It did give, that was the string that said invalid registration code. However, when you use a semicolon, you can change the comment for whatever it is. And Immunity decided not to actually yeah, it's not even in the patches. Sorry about that, guys. So for some reason, Immunity decided to not reset that, and it should have. And so that was where it said invalid registration point. And then right here where it says success is where it actually said something like congratulations, or it said successfully registered.
You can see it in the bottom.
Where?
This was Unicode. Congratulations.
Oh, there we go.
Mouse drive.
Yeah, you pointed out. Thank you. So it actually said this right here. Thank you, John. And then right down here, it said invalid registration code. So that was where it was. Sorry, guys, that was my bad. I cleared it out, and for some reason, Immunity did not reset that. Sorry about that. Okay. So now that we can actually start working on this one, sorry about that. So we're seeing here's the failure point, and here's success. So we're just going to mark those 2 points. So do you guys remember what we did for the last one?
Is there any way you can just search for like success and failure? So I found that.
I expected it to reset those, and that because it shouldn't have kept those. I don't know why it kept those cached. However, it did.
So you can keyword search and like this.
You should be able to. Yeah, user defined comment right there. So I would have seen. Oh, look, failure. Right there. Yep.
And you found this after what? I wasn't here when you found it.
Oh, he was just going down.
I was just going through it and I saw it. You can. What I was saying is you can actually comment anything yourself. So all you have to press is semicolon, and then you can re-comment something. The comment that Immunity puts in is Unicode invalid registration code right there.
Yeah.
And then up here instead of success, I was just experimenting around with it yesterday. However, I was expecting it to reset, and it didn't, which I'm not happy with. But anyway, so we have the failure here and the success here. So do you guys remember what I did last time to just kind of look around, or is anyone brave enough to just kind of hop up here and see if they can find something?
The jump.
Yep. So you guys got it. So it's the jump, and see if we can find the jump that is either jumping up to success, and it's either failing to jump to success if it's a failure, or it's jumping past success down to failure.
There's a jump above. There's a jump above success though. But the JG.
Yep.
Yeah.
So we see that that's actually jumping right here through that line.
Short jump.
So that's a short jump. So it looks like it's just jumping over whatever's happening here. What was that? Louder so the people on YouTube can hear.
Jumping past the library.
Yeah. So BJ said jumping past the library call. Anything else that people see? And then, yep, there you go, JE. That's kind of hard to see, and that's because for some reason Immunity is not clearing its cache, and it's keeping it gray because I changed that one before.
Oh, yeah.
Sorry about that. It should be red. However, if we follow that line down, we see that it jumps right past success.
It jumps
and then jumps down right before failure, and it can continue on. We also see a jump here, which if we assume that it took this success, continued on, we don't see any other jumps or anything else like that. We see that this jump jumps past failure after success. So we kind of have an idea of the flow of the program, which Python actually does include a graph. I think I'm hovering over that right there. Yeah. So we can actually look at this graph, which it's not using correctly right now. This graph, this is a very terrible graph right now, but that's because of what I have selected. If you select certain things, you can actually look at the graph and it will properly graph it out for you. However, I think the EIP has to be there.
Does the graph thing go bookmarked or the thing that you selected?
I believe it's the thing I have selected. However, I can actually just go to breakpoint and I can go right there. Yep. Okay, so we have, although this is the one I don't actually need. Okay, so we have one on success and one on failure. And then we have this jump that John pointed out that jumps past success and then down to failure. So we're going to break point there, and then we're going to run it. So we're going to go back to running it. We're going to press register, and oh look, it hit that breakpoint. So now it's saying, you can see also right here, if you can't see that blue line, it's saying the jump is taken currently. So it's saying that's wrong, so it's going to jump right past success. Now remember what I was saying again about watching this line, about how it could jump down but then jump back up. So we should actually look at this because we see this is an endpoint and look at where that's coming from, which is actually just right here, so we don't have to worry about it. Because what it could be doing is this jump could be jumping down to like say here, and then this line be a jump right back up to here, and then it's still hitting success. So all we did was put a breakpoint and we looked over registers and all sorts of other stuff for no reason. However, because while we're still here, we can actually pull up the stack and look what's right there. However, that doesn't look like quite the right formatting.
Yeah,
So we can actually scroll around and we should be able to see. Yep, there you go. So John pointed out that correctly. That's the string I entered right there. If we step through it, we should actually be able to see this in the correct formatting. However, that's the right number of strings. It's just hasn't been formatted correctly yet. And that's because of how this program was made, which you can see up here. You can actually see that it's doing, basically what it's doing is it's moving around strings. It's like, he has a dictionary way up above. He has an entire basic ASCII dictionary of text, or of letters and numbers. And then so what he's doing is he's generating that password relative of that dictionary. And then he's taking that and then generating it little bit by little bit. So I think he's actually generating it 1 byte at a time, which is going to be 2 digits at a time that we see. So that's how he is actually generating that. Anyway, so now that we're actually at this breakpoint, what should we change this to? Or should we just let it fail? So do you guys remember what JE is? Yep, that's right. So it's doing a jump if equal to. So it's checking if this DI is equal to this BX. And basically what it's doing is it's setting a flag over here, one of these. And then it's basically setting it to something. And then the jump will jump based on what that flag is set to. Yeah. So do you guys remember from that slide? JNE. So it's jump if not equal to. Yeah. Okay, so we're going to reassemble that. And you see how it actually highlighted that digit. And it's now blue. And then we're going to have to cancel.
Why does it put J and Z, by the way?
That just says jump if not 0, which I think is actually, Immunity is being smart about it, and it's actually referring to, correct me if I'm wrong, VJ, it's referring to that flag, and that may be a binary flag.
Yeah, flags are, flag register is just a collection of 1 bit. flags that are stacked together. So if there was carry flags and 0 flags, so that's just checking if it's not 0.
So yeah. So it could actually be JZ, and it would have been the same as JE in this case, correct? Yeah, technically. But in this case, it just changed it to J and Z because that's what it knows for that flag for that compare. Anyway, so from here, we're just going to start it back up again. And we see we hit the success, and we hit play again. And I'm going to Alt-Tab so we can actually see it. And congrats. You got the password. Good job. So that is 5. So we can actually exit out of that. And then we're going to load up 6.
Just curious, do you ever get the actual registration code?
What it showed right there was the correct registration code. It wasn't just formatted.
Just not
correctly.
formatted, right?
If you would have put a few breakpoints before it, you could have actually seen the correct formatting, and you would actually see it pop into one of the registers. I haven't been paying too much attention to that. It was actually a mistake I made a while ago. Was I thought before I'd learned to properly look at the stack, I kept only looking at the registers. And the thing is it can pop into the register for just a single instruction, and then the next one can remove it or overwrite the register rather than
So what
remove it.
format was it changed to? If you're saying it wasn't the correct
Oh, the formatting, basically the hyphen was in the wrong place.
hyphens were in the wrong place.
The hyphen was just moved over.
Oh,
That's
so,
all. It's correct. Other than that, though.
okay.
Can I make a comment on this?
Yeah.
So the registers by name, EAX, etc., are just symbolic names the CPU uses. The CPU internally has about 167 nameless registers. So when Ian said that the register would switch out, that's the CPU referencing a different register with EAX or whatever. But it's all relative per instruction or context.
I don't know why the registers aren't properly. There we go. Now you can actually see the title of the registers. Okay, so this is app 6, which when we see it first starts up, hasn't fully started though, looks like that. So it looks like it's a command, which means this one's also totally different. So we're gonna start that. And then when we Alt-Tab to it, we see that it's just saying password, just as simple as that. And so if we enter something, I'm just gonna go with ASDF again. Wrong. Press any key to continue. Okay. And it boots you out and closes the application. However, immunity stops it from actually fully closing. So we're actually just going to restart it. So we can actually see right here, we're going to start it back up again. Once again, it's asking for the password. So we're going to pause it. And then once again, we're going to go to the application. Now that we're here, we're going to go and we're going to search for all reference text strings. Oh my gosh, what is this?
What?
Wow.
Okay, so a little bit of a hint. I've actually talked to Joe a few times since the CTF about these applications. And he actually helped provide a little bit of insight into them along with giving me some idea of what the ones I had completed at the time, how they were functioning.
I wonder what the password is.
It's not that.
It's not.
It is, I promise you it is not that. It's not any sort of type of thing like that. It is completely obfuscated. Obfuscation is basically what he did was he, how to explain obfuscation?
Obfuscation is essentially a process of changing something from one form into another, but have it still operate the same as it were in the original form. In the case of text obfuscation, it could be something as simple as
So
a
we changed
XOR.
it to say that.
Yeah.
Yes.
So basically what it's, now why it's actually in here so many times, I don't know exactly. I haven't seen his source. I would love to see a source, but he's not giving that away. Basically what it's going to do is somewhere in the source code, he has an algorithm that turns this into the actual password. However, we don't have this algorithm or whatever method that he was using. Like VJ said, it it could be a simple XOR, which is a mathematical logical operation of bit. It could be a bitwise XOR for all we know. However, we have no idea. It could also be an insanely large complex algorithm that would take years to crack. It's probably not, but it could be. So we're not going to mess with this because he said, he told me, I promise you, you will not decode that. It will not work. So I'm going to trust him on that. So we're going to look through this, see if we see any strings. We see some true and false, something with write binary, read binary, read plus binary, append binary. I don't know what those are doing. It's writing something. Could be a temporary, or that could be probably how he's changing all of this. So we're going through. We're seeing that for some reason he put months and dates in here. I don't know why. We see infinity, not a number. We're just going through. There's a lot of strings in this. We see POSIX. Anyway, so we don't see too much that's really obvious. Yeah, exactly. There's no low-hanging fruit on this one. So it's going to take a bit of work. So we're going to go to this. We're going to go to the first one here. And I'm going to move these registers over because we're not using them right now. So we can actually see what it's doing is it's moving this, moving that, and it's calling something, hint, nothing that interesting. Anyway, and so it just keeps doing this. So we're just going to scroll through. I'm going to go really fast because this is actually a kind of a long program. You can see right here that this thing is giant. It is huge, guys. So we're going to go back to the strings right here. So we can see that it's doing something with this password. It's moving, it's calling something. It's calling somewhere in the application. We can actually see. And there it actually gives us the address. And we could try to look through that and see if we could figure out what it's doing. Hint, it's a pain. It's going to take forever. It's pretty hard to understand anyway. So we're not going to deal with that. However, that was after like me working on this for way too long. Anyway, so we see that this whole thing, anyway, this whole symbol right here, we can actually see this through the dollar, and then the ending right here. This is a call. So something called to this point, and this is where it's being called to. And then right here is the return. So it returns back to the point at which it called something.
What's the NLP right there? What?
NOP? You remember what NOP stands for?
No observation.
Oh, yep, that's right. No operation. So basically it does nothing. It reads that byte, it says, okay, next. You want to go over some purposes of NOPs? Okay. They can be used to align things, and they're used very heavily in exploit development.
Yeah, it's the compiler will put NOPs in to make all of the addresses line up and make the compiler happy.
Yeah. There are also other reasons. Like I could insert a NOP. I could actually overwrite something. I could overwrite this with a NOP, and it would skip that. It would completely ignore it. Generally not a good idea. Because if you skip over something very important,
The stack is in a state that's not expected by the next call, and everything.
It's just gonna
Yeah.
crash.
it can crash the program immediately. It can really mess things up. Yes, it can also do that. So also, again, why it's good to do this on a virtual machine. You want to say that louder?
Oh, there's a funny ongoing joke that using 7 bytes of assembly, you can format your entire hard drive. And in some cases, that's true. Doing things like placing NOPs where they shouldn't go causes undefined behavior. So,
Now, that doesn't mean if I put a NOP here, my hard drive's gone. However, if I put a NOP in the correct place,
It's
gone.
possible.
I could ruin like a core system DLL that will make Windows not work whatsoever, like at all. Once again, why you do this in virtual machines? I'm being very, very bad right now by not doing this in a virtual machine.
You guys live on the edge.
Yes,
Living on the edge.
we'll go with that. No, I know this application pretty well. And yeah, I know it's completely non-malicious, and I am not going to be experimenting like putting NOPs just here and there. However, for those that don't know, if you have a virtual machine running and you were to do that and you were to snapshot it before, use your snapshots when you're on your reverse engineering machines, you could format the entire hard drive and you just say revert and it's completely back. You can just get back to working on it. So, thank you. Anyway, so we have here, see that this is calling, this is a call. So if we scroll around and we just look around, I'm going to do it pretty quick. We see that there's all sorts of stuff up here. See it's doing a lot up there. And we see down here, okay, so we also have another call right here. Hold on, I'm going to breakpoint this. Breakpoints are also the lazy man's reference points. Because I can put a breakpoint here and wherever else, and I can go to the breakpoints tab, and I can look at all the breakpoints, and I can just go through them. It's very lazy, and it's not proper, but it works.
That's the title.
What? Oh, yeah. Anyway, so I'm going down here, and I can also see this is a whole very, very long function right here that it called to. I can see through right there. And then I can see down here at the bottom, it is doing a return right there. Just like, oh, it's over. 1 second. Thank you. Okay. So I'm also going to put a breakpoint here just because it's kind of odd. We have it doing something to this obfuscated string, and then we have it doing something else to this obfuscated string. And then down here, we also see this WNG that we saw, which is part of this, but it's also part of the word wrong. So we just see that it's 3 points here, here, and then up here. So because we don't have any other clear direction, we're just going to start with that. We're going to start the program, and we're going to see if that works. So I hit start, and I'm going to go back. We're going to go with ASDF, which obviously does not work. Okay, so it hit a breakpoint, which was right here. So now this means, we don't know exactly what this means at this point. It could mean that this is just part of its normal navigation. It could mean that I got it wrong and it's about to exit. So at this point, we're just going to have to find out. So we're going to step through it once more, and then we're going to see that it says wrong. So we're going to restart it. And rather than exiting out and exiting out of everything, if you restart, it's going to try to keep your breakpoints for you. It will try. Sometimes it doesn't like it. Sometimes it really complains at you and is just like, no, you're wrong. Anyway, so this time it kept the breakpoints, and it actually, on first load, it hit this breakpoint, which is interesting, to say the least. So we're going to try this again. But this time, before we start by putting the password in, we're going to say, okay, so it looks like it calls to, yep, that one. So it hits this one when I get it wrong. So let's see where it's doing this call. So we can actually see right here that it's doing a call to 401A-D8, which we could either scroll to or, it looks like we can't double click. So Control G once again, which pops up this window. And then so we're going to go to, and I unhighlighted it, sorry. So we're just going to go to 401A-D8, and we're going to jump there, which was actually right up here. Shh. Anyway, so we have it, we can see that it's doing this call. However, we can also see that it's doing a call down here and a call here. And if you were to scroll to these, you would see that there are these other points here and here. So we can see that those other 2 points are referred to right here and here rather than here. Sorry, here. So this call is right here. This call and this call are the 2 down below. Make sense? Everyone's tracking? Great. Okay, so once again, Immunity is giving me away. Thanks for nothing. And it is showing what jump. Actually, I don't know why that's highlighted. Anyway, so if we see that this is actually a call in itself, we're just going to assume. Sometimes you have to go through step by step by step by step and by step, and it can take a long time. However, none of these are actually too long to reverse. So if we're assuming that this is the call, nope. We can actually compare that. So those are the same. So we can see that it's calling that. And then when it gets done, it jumps here down past these other two. So let's just try putting a breakpoint there. We also see that this calls to that second one, and this jumps past this third call. So we're going to put one also on this jump, okay? Because we're just taking a look at it, and then this jump passes this last one, but that one doesn't have anything to do with the obfuscation. So we're just going to assume right now that it's not actually going to change too much. So we're just going to look at these 2 points, and we're going to start and see what happens. So we have this. We're just going to do that wrong password once again, and we're going to hit enter. Okay, so we can see now that it actually paused right here because it hit this jump. And we can actually see that it's saying the jump is not taken currently, which means it's going to continue down to the second call, and then it's going to go to this jump, and then it's going to go to this next call, and so on. So we're just going to see how it goes normally and kind of get a better idea of what it's doing here in the assembly, so that from that point, we can get a better idea of what we should edit to change. So we're going to do it once more, and we can see that this jump is then taken. We can see that this call is made down to there, which is the last one down here. Did I totally scroll past it? Yes, I did. Yeah, it's right here. So that last one is to right there. Anyway, so we're going to say, just to see, what if we change that to jump if not equal? We want to see what happens if we call them all. Just to let you know, if we let that happen, it's going to just exit out after that. It's not going to hit any more that we'll see. So we're going to change that to a jump if not equal. Symbol. Okay, so now let's test that, and now we can see that it's saying the jump is not taken. Let's try that. Oh, and it hit this spot now. And we're going to go through there. And we're going to Alt-Tab to the application. There we go. We got the password. Now, that took me like another 30-some steps when I was doing it. I went through and I ran through the program like 5 or 6 times before I actually changed anything. But that's just because I was trying to figure out where exactly it was going and what the flow of the program was. And that's really important, actually. I'm just kind of skipping it because yeah, I'm just trying to do this for time's sake currently.
Just curious, once you put the password, did it spit out the flag? Or
this is this is the flag right here.
That is the flag.
This
Okay.
when he wrote them, he wrote it to say usually in CTFs the format is flag or some word, curly brackets, and then the flag is inside that. However, Joe decided he was going to write the flag as saying the password is. I don't know why, but he did. That's okay. So we have that. We now have app 6. It's done. Question?
How do you start a SAMA program or whatever I'm writing in a program? How do I stop my program from being
That is a question for VJ. And if you want to wait till after, I only have one more application to go, and this one's actually really quick. Like this is way quicker than I should have taken on this application. I can give it over to VJ to answer that question, which he knows too much about. He actually wrote an application that me and Steve and a couple other people tried to reverse, and so far no one's been able to even touch it, really. So, and it killed Steve's machine.
That was an accident, but
So you say.
No, it
No.
crashed my VM.
Oh,
wasn't the intention.
Okay, so we're going to run this, and we see, oh look, what is this? It's nice and bright blue. What is the password? Pro tip, it changes constantly.
I love that.
Oh, and once again, with the previous application, and with all the previous applications before it, there are multiple ways to figure out what the password is, including, as VJ asked me earlier, there are things you can do to actually watch the stack for certain things to happen. You can trace a program, which basically is saying when certain conditions are met, breakpoint, including I could say when a Unicode string goes across the register, breakpoint. Just
So you
break
can see
wherever
that.
you are.
So you can.
Because I know that he is using a Unicode string for all of everything, which would have been an interesting way, but there you go. So what is the password? Pro tip, it changes constantly. This means that if we were talking about patching every program, like I said, how you could easily do with the second one, how you just rename the password in plain text right there, or in this one, or in the fourth one, how I was saying you could just change one of those bytes for the instruction. That means in this case, where it changes constantly, you would have to change the assembly instruction to change a jump or something so that it will not, it will continue to change the password, because that's a whole other thing that's way more complicated to figure out where exactly it's doing that, what it's calling, what I can change, what I should change, how I should change it. All these things are way more complicated, and VJ can definitely attest to it would take a lot of time to figure out how to do that. So we're going to just stick with the whole jump. We're going to say, because all these programs have come down to just one jump, some programs come down to many, many, many consecutive jumps that is taking many compares. But for this, we're going to say one. So pro tip, it changes constantly. So in this case, I'm not even going to see what it's going to do normally because, or actually I should, because I should see what it returns so I know where to go next. But I know that there's going to be no chance of me guessing it, no chance of me trying to figure out what's right. I'm just going to have to try it. Wrong answer, try again, and it exits out. So we're going to restart. What? Yes, it did say that. Sorry, I'm a loser. I got it wrong. That's what I get for showing you people. No. Anyway, so it said that. So now we're going to go to the application. We're going to search for those text strings. We see a lot of nothing. And we're going to go through this. And we see that. Oh, yeah, there you go. Good job. So that's about as close as a chance thing as we're going to get, and that's not going to help. Strings like that are going to be strings that are contained in the program that are referenced. So basically, something is going to reference this point because all this is a plain ASCII string saying loser, wrong answer. Before, what we were looking at where it said password, those were comments on it because that point of the code is referencing that string. Okay, so if we are going to just scroll up, we're going to see if we can find any sort of reference to this. Actually, you can actually go find reference to nothing. Oh, darn. So we're going to go back there. We're going to go to view. We're going to go back to the application. And I'm actually just going to scroll through this really quickly. And you'll kind of see that this one's a bit different than the others. It has a lot of this DB0. Normally, a DB00 is going to be an empty array or an area that is going to be, could be used or filled. But we see like the entire thing is like that. And there's not enough in this currently, except this, which actually is just the ending of a program. That's basically just the program ending. There's not enough in this for the program to actually do anything, much less run a command line. We know something's up at this point. So what would you guys think we should use to check the program? See what's up with this program. We used it at the beginning. The detected easy? Yeah. So we're going to load that up, and I'll actually show you what the program looks like right now.
Oh, wasn't here considered.
Oh, okay. So the detected easy, I was going through, and I can give you guys the PowerPoint to show you how I used it for the first few applications. So it analyzes any sort of file for whatever.
There's technical definition up there.
Yeah. Okay, so it analyzes it for all sorts of things. So including, okay, hold on. I'm going to load up the first one. I'll just show you guys the first one for those who weren't here. Okay, so here's detected easy. So we can actually see through this, the type is a portable executable. We can see that it is an exe 32-bit. And then we see that the compiler was Visual Basic. So those programs were written in Visual Basic. We can also look at imports and all sorts of other things. However, in this case, we wanted to just look at strings. ASCII, oh, look at all these useless strings. Now these are helpful. All of these are Visual Basic things, like they are all Visual Basic instructions or standard naming symbols. Well, those are symbol names, and then the other ones, like form1 and stuff like that. Just defaults. Those are just property names. So if we search through this, we see that the first string is way too easy. And yes, that was the password. And yes, that was that easy. There we go. We solved application 1. Whoa. Okay. Yep, just like that. Anyway, they have all sorts of other things like scripts and plugin supports. And you can look at entropy, which I went over. And I was talking about entropy is the predicted, in a way, it's kind of the possible predictability of the future of the program, basically. So entropy, if I had pure hex of just zeros repeated, the entropy would be 0. It's completely 100% predictable. You have 0, 0, 0. What are you predicting comes next? 0. What are you predicting comes next? 0. You're right all the way. It has an entropy of 0. It's completely predictable. If you were to have like 8 ones followed by 8 zeros, the entropy is of 1. That has nothing to do with the binary of the ones and zeros. It's that predictable. An entropy graph shows you the entropy at multiple points during the program. So here's what the entropy of, here I can actually show you what, I'll pull up the slide with the entropy graphs on them. Okay, so here is app 1, 2, and 3. So we can see applications 1 and 2 are very, very similar by these areas. And then application 3 is very different. Okay, so we have, this is application 1. And if we go back and we load application 7, first of all, if we look at entropy, we see that it's this. It's 7.8 or something like that through this area, which means that it is not normal. 8 is true entropy, which is technically impossible. It will always be like 7.99999 repeating for reasons.
Is that where the whole like DB00 thing was all at?
Yes.
Okay.
That's correct. And then you can actually look through here and you can actually see the different sections. So we can see that that section was all, there was something up with that. Anyway, so we can actually look through that and we see it's completely, that's almost completely true randomness, which means it's either encrypted, it's encrypted within itself, or it is packed. Hint, it says UPX, which is the, oh, hey, say that louder.
Universal executable packer.
Okay, universal or packer of, I don't know. Yeah, it's UPX. It's a packer. So basically what packer, you want to explain packers? You can explain it better than I can.
Packers are applications that have algorithms that take an executable, squish it down, and then wrap it. So when you run the packer, it unpacks it in memory. Sometimes it doesn't, and then runs the application itself. It's a way to get undetectability for malware or just compress your application a little bit more if you want to save space.
You can also package in libraries with your executable,
Yes, which makes it stable.
which means rather than saying, here's this big zip folder, unzip it, and then run the executable with the exe and all the DLLs, this packs everything into one. However, this also makes it a pain to reverse. Actually, it makes it basically impossible. You can't do anything when it's like this.
It's always fun to watch it.
Yeah, thanks. I may have struggled with this for a while before I looked it up in die, at which point I saw it was UPX, and then it was
So one of the first
pulling.
things you do before you start this is usually you run a static analysis, which Guile does, and it actually
Yes.
says, it did say packer on there, right? When you click-
Yep.
Yeah.
Yeah, if you look up entropy, we can actually see that it's packed.
Yeah, so you see it's packed, and it also tells you when you click it, it tells you UPX, right?
No, it shows you UPX back here.
Okay, then so right there, then you go use it, and then you could later on do your dynamic analysis.
For packers, generally look up what packer is being used, download that same packer, unpack it. In this case, it's one command line. It's like upx.exe slash d for like dpack slash or tax something, and then the application. Anyway, so I have it fully depackaged up here. Yes?
Sometimes too, if the packer is not too complicated, you can just do 7-zip and extract it. So,
Yeah. I
yeah.
I could have possibly done that. I don't know.
I don't
Whoops.
think it works on UPS.
Okay. Well, that makes me feel better. Thank you. So I actually already have it unpacked right here. So we're going to open this up and we're going to look at it in Detected Easy because you can pack it multiple times over different packers or over itself. So just because he's already packed it, I don't trust him. So we're going to see what it looks like now. So we can now see that it says C --, which BJ is laughing at. And then we see that it was used polink, and then it's a 32-bit executable now. So now we should be pretty safe to see how the program works in Immunity. So now we're going to try to load that up. And that's in here. Just a second. So there's that program. And then now that it's started, oh, just a second. My firewall is telling me it's not a normal application. And I'm telling it to shut up. Okay, so there we go. We have the program running. And if we go through here, and I'm going to pause it, and then I'm going to go look at the application, we can actually see, now doesn't that look like normal assembly, right? Now, let's see what happens when we search for reference text strings. Oh my gosh, look, real strings. Yay. So look, we have wrong, we have congrats, we have all those, we have loser, we have all the stuff that we were looking for. We have the dictionaries, we have all the normal strings. So there we go. We now know that we are much more likely completely done unpacking it. However, there still could be sections that are encrypted and so on and so on. However, if we were to throw it in die again, we would actually see that the entropy is much, much lower to a normal level. So let's look at the wrong answer once again. So we're going to pull this over even more. So we actually see wrong answers right here. We can actually see that they're in these little groups. And then we actually can see password and congrats. So who wants to try to Actually, someone come up here and fix it. Yeah, you guys have seen me do it a few times. Someone come up here and fix it. Yeah, want to try it? Anyone? Anyone, or I'm picking someone.
Steve, yeah.
Yeah, I vote Steve. I vote Steve.
I'm the only
Can't hurt to
now.
try.
Apparently, I got the only
Oh,
balls
it's
in here.
It's okay. Okay, so now that we have this right here, we have the congrats and we have the wrong answer. What are we looking for?
Above that.
Above that? Okay, what command, what instruction are we looking for?
I'm looking for so far equal to equally, like jumps.
Yes, correct. So we're looking for jumps. So what jump do you see that is so very near?
Up here. Because it goes past this.
Well, we see we have it right here and right here. So in here, what jumps do we see?
This one.
That is an entry point, so that means
Oh.
a jump went to that point. However, we're looking right here for instructions, so a jump is going to start with a J.
Right, it's up.
It may not be. Click right there.
Oh.
So if we click on that, we can actually see
That's
that this
the-
jump skips right past congrats and goes right down to loser.
Okay.
That's the jump.
Does not equal.
Is not equal. To
That's
the
jump if not zero.
not zero.
Yeah. So in this case, it was actually right there. All the others were more complicated than this. This program's complication was that it was packed.
Okay.
So,
Like a horrid mess.
okay, go ahead and double click on that.
Good job.
Look prettier
Quicker.
as a. Yeah, but you can't do anything with it like that.
Oh, just like
It's gotta be like-
you have to pause it.
And I gotta try to jam that in
There you
there. So.
Okay, so now that we know that that says jump if not zero, change that to jump zero.
So take out the end.
Popped it out. I was like, oh my
And then click
God.
assemble and click cancel. Okay, now it's hard to see on this monitor, so it's right there. Okay, so now that we have done that, we're going to go back to playing it. And then we're just going to change over the application, type in whatever you want. Just wrong password. Enter. Congrats on guessing the answer. Hit OK.
That's how it should always
And it actually, for a brief second, pass is Ratfink, I think is what that says.
Or I think, I don't know.
Yeah. Anyway, there you go. We have got all 7 answers.
How come
Got
that?
all the
How come
flags.
that one acted differently at the end?
How do you mean? Oh, you mean how it like went
It just
behind?
went behind.
Accent. She accidentally clicked the
Oh,
immunity. That's all.
just wanted to make-
No, it's normal. It doesn't do something weird. Oh no, it's all good. You did great. Thank you very much. Okay, so we have now gotten all 7 applications. That is the basics of reverse engineering. Once again, you can use immunity on any application. If I wanted to try to reverse engineer, what's a paid application? Windows.
Yeah, Windows and Photoshop.
You could try and do that. Yeah, you could.
Wouldn't be easy.
It is not. It is by no means easy. However, you could reverse engineer Windows. You could reverse engineer Microsoft Word. You can reverse engineer whatever. None of it will be even close to how easy these are. Even one of these last ones are pretty easy.
when you start getting into like protection mechanisms and stuff.
Yeah, there are some very basic protection mechanisms that are very, very difficult to get past. And if you don't know exactly how to get past them, they will start rewriting that current operation with invalid opcodes, which is these. These are called operation codes or instructions. They'll write themselves over with invalid opcodes, basically ruining the instructions and crashing the program itself. So,
Wi-Fi one.
yes, that's a very basic protection mechanism. So that's just an example of some of the stuff it can do. But these are, once again, this was the basics, and we started touching into more of the mid-level-ish stuff. However, I believe this should be enough for you guys to just go on your own and kind of mess around. And once again, if you want, I can write down whatever email addresses you guys have, and I can send you guys a zip file of all the stuff just together. So if any of you guys want that, just let me know, and I'll write down your email.
Maybe next week we can do buffer stuff or something. That way they can actually get their hands on the DVD.
Yeah, we could definitely do that. Anyway, so
Oh, and we're doing the DEFCON. DEFCON qualifier starts 5 o'clock on Friday. I have it on the board. There's posters everywhere, sort of.
Yep.
And we're all going to be meeting in here. It's 48 hours.
you don't have to do it straight, but if you want to, you can.
You can die if you don't do it for free.
I slept on the table.
But we have a lot of fun when we do them. I would recommend that you guys try them out, at least to see what you're interested in and what paths you want to maybe go down or whatever.
And reverse engineering is a very small point of CTFs.
It is.
They are so much more. They are web, they are hacking, they are
Problem solving, whatever it is.
they're basic quizzes too. I mean, there are basic quiz questions, like from famous phrases and stuff. I mean,
We all have
they're
a lot of
literally
fun
everything.
when we do it. So
It's a lot of fun. It's a great challenge. All these I got from a CTF. I have actually a whole folder just full of different challenges here and there. It's great. It's a lot of fun. You should all participate. You can sign up at legitbs.net.
There's a link on the official forms, right? As well.
I didn't put one there, but I can.
Oh yeah, you should.
Yeah.
it's on the poster too, I think.
No, it's not. Kenny left it off that one. Yeah, thanks, Kenny.
Okay, there's that one.
Sorry, Kenny. Anyway, so legitbs.net, when you sign up, there is after you enter your username, they're going to ask you for a team. Team is layer 8 with a capital L, no space. Password is layer 8, same as the username, CTF69. And there you go. So please sign up for that. Just meet us up here. We're going to be here up just a little bit before 5. It's a lot of fun. I've learned a ton from CTFs. I recommend everyone participates. And that'll be it. And I'm going to stop the broadcast for now. Have a good night, everyone.
Awesome.